So now we're dealing, this last format would probably get used over amount concentration sometimes. If you express the amount concentration of very dilute solutions, you might get 0.000001 moles per liter, incredibly small numbers. Okay? So both scientists or the drugstore, a water bottling company might use parts per million, parts per billion, or potentially parts per trillion, but that one isn't in this course, but you could easily take the trends we're doing and understand part per trillion in post-secondary. So we have to let go of percent, okay? The most common errors, you want to go solute divided by solvent, or sorry, total times 100, but that's not what we're doing. We're keeping the same format, solute over total, but we're going to express it in mass units, okay? We're not going to do anything in volume here. So in parts per million, we need to use units that are 1 million in the difference. So we're going to focus in on your table that's in your Alberta data booklet on page 3. We've got all the prefixes, and we need million differences. Now, just before I get to the million, talking about this table a little bit, you have to realize that the base is missing. And it's missing on purpose because the base has no prefix. So there's no reason for them to put it in. But that would be the 10 to the 0. We've all these 6 power jumps, minus 12, minus 9, minus 6, minus 3, and then it goes right to plus 3. Okay? So when you're counting your 1,000 jumps, you have to realize the base would be located where I put it in blue. Okay? So you can use any combination of units that have a million difference, which a million is 10 to the 6. So I've pre-labeled a couple options. So milligrams is 10 to the minus 3, and kilograms is 10 to the 3. There's a 6 power difference here, which 6 powers is a million. 1, so one option is to use milligrams over kilograms. We'll do parts per million. Okay? 1 milligram in a kilogram is 1 in a million. Okay? Another option that can work is micrograms, which is 10 to the minus 6. So if we go up 6, we're just at the base, which has no prefix. That's also a million difference, 10 to the 0 compared to 10 to the minus 6. Okay? Now you could use other combinations. I'm not going to, okay? But in theory you could use, giga and kilo have a 6 difference. Okay? We're not going to use anything that big. When it comes to parts per billion, same type of thinking, but we need units, a billion in the difference. Okay? So I'm going to tend to just use one combination. If I use micrograms, which is 10 to the minus 6 for my solute, I need the total solution to be something a billion times bigger, which a billion is 10 to the 9. So we have to go up 9 powers. So minus 6, we all have to go all the way up to plus 3 as our power. Okay? And that's a billion. So if we think of 25 parts per million, you could express it in either of two ways. You could think of it as 25 milligrams, so that's not a lot, a few specks in a kilogram. Or you could think of it as 25 micrograms in a gram. Either way, we're talking about a very small amount of solute in our total solution, the total mass. Now we are going to have to do a fair bit of converting, so just giving you some guidance on doing converting. If you are switching units, so maybe you want milligrams or you want kilograms and you have to go up or down converting your units. Every time you go up one of the rows, so if you have micrograms and you want to go to milligrams, when you're going up, you're going to a bigger unit. So let's say we're going milli up to kilo, and we want to express, you know, milligrams and kilograms. You're going up to a bigger unit, so you're going to end up dividing. Okay? Every jump you make in this table is a 10 to the 3, which would be 1,000. So the base unit to kilograms would be divided by 1,000. Okay? Grams to kilograms. Okay? Milligrams to the base unit divided by 1,000. When you're going down and you want to convert units, you're now recording stuff in smaller units, and that's when you multiply by 1,000. Okay? And you'll see some examples coming up of converting to get the units we want, be it those, or we want to get those units. Okay. The format and layout is going to be pretty similar to before. So our first question, what is the concentration in parts per million when there's a little under 25 milligrams of lead detected in 25 kilogram, in a 25 kilogram river sample? Okay. So that 25 kilograms is our total sample. It's not the solute, it's everything. Okay. So we're doing a concentration. It's always a ratio, whether it's moles per liter or volume to volume, or in this case, it's parts per million. Now, we'd want to think of what units. We need a million in the difference. So that milligram per kilogram, we already have milligrams, so we must well stick to my first green circle, which I'll now make blue. Okay, that's going to be easier than the second option. So 24.6 milligrams. Once I pick milligrams, I'm forced to pick something a million times bigger, which is kilograms. And we don't have to convert. Okay? The total solution is already in kilograms, so this is just plug and solve. Okay? But don't just divide the two numbers without thinking of your units first. Okay? There is no times 100. Okay? You take your numbers, you divide them, they both have 3 sig figs, so I'm going to report 3 sig figs, 9, 7, 6. And we're going to replace those units. These units represent a milligram in a kilogram is a part per million, and you just see ppm written in afterwards. So we're pretty close to 1 part in a million with that 25.6 milligrams and a little over 25 kilograms. So similar to before, the percent, you just have to watch your units. Second example, it's still parts per million, but we now have 25 milligrams of sodium, probably sodium ions, in a 400 milliliter water sample. And we can't tell by looking at the 400, but I'm telling you all of those digits were measured. Okay, 400 is a bit ambiguous. You know, what was measured with those end zeros? And I'm saying all was measured to the nearest mill. Okay. Set up our ratio. Our solute is given in milligrams again. So if we have our solute in milligrams, we need our total solution in kilograms, which we don't have. We don't even have mass units. So we've got a little bit of converting to do. Now water, Every milliliter is exactly a gram. So 400 milliliters would be exactly 400 grams. There's no need to weigh it. But that's still the wrong units. We've got to convert grams to kilograms. Okay. Now you could use the factor label method, but I'm trying to get you used to just using this table and doing converting quickly. We're at grams, which is the base, and we need to go up to kilograms. One jump up, and every up jump is 1,000. So it's divide by 1,000. Okay. I think getting used to that table can let you convert faster. Okay. So when you divide by 1,000, you get 0.400 kilograms, and I'm telling you those end zeros are significant. Were measured. Okay. If I didn't tell you, you'd probably think that's just one sig fig. Okay. So we have our kilograms, so now we're all set. Grab your calculator, do the division. The solute only has 2 sig figs, so I'm going to go 7.8 and replace our units with parts in a million or parts per million. Last question. Relates to the information above, so I'm going to leave that visible. We're still in B. How much sodium would be in 100 kilograms of river water, knowing the concentration above? So this is solving for a solute. I'm going to do the exact same layout that I did before in the percent lesson. So how much sodium, how much solute would be in 100 kilograms. So that's our solution. So all of these, I'm going to take our concentration, turn it into a ratio, multiply by solution, and that's going to tell me the solute. Not the only way to solve these. Many come up with other ways. I teach one way. So how much sodium, how much solute, so that's our question. I'll put in X, is in 100 kilograms. So that's our solution. Knowing the concentration above. So we've got to decode that concentration into a ratio. It's just not a percentage anymore. So that is 7.8. And we've got to replace these ppm units with units that mean parts per million. Don't divide by 100, it's not a percent. So you have to think of what units do we want to use. I already see kilograms I put in my solution. So that would lock me into milligrams per kilogram if I'm going to use those solution units. So 7.8 parts per million is like milligrams per kilogram. Once I put milligrams in at the beginning, it means my answer is going to be expressed in milligrams. If everything is set up right, the units should work out. Kilograms would cancel kilograms, and the milligrams would pull forward as our answer units. Okay. So the sodium is going to be 7.8 times 100. So 780 milligrams. Now I rounded this. I was treating this 100 It's a bit another ambiguous number. Okay. On tests, I don't put in numbers like 100. I remove that ambiguity. But assuming that was 100 measured to the nearest kilogram, the solute only had 2 sig figs. So that's why I rounded this to just 2 sig figs. Okay, but we had some ambiguous zeros in this lesson. Okay. So this is parts per million. It's what students might make the most errors on, but it's largely just math, realizing units, and converting units. You don't get the meaning of parts per million and billion on a formula sheet. You have to know to go to page 3 and remind yourself of units that are a million or a billion in the difference. Now, we're pretty much always using parts per million and parts per billion with water. So often you'll want to think of parts per million or calculate it in milligrams per liter. This is just coming from milligrams per kilogram is typically what you would expect. Okay. But for water, 1 kilogram is 1 liter. You can just switch the kilograms and the liters freely if you want in terms of doing your calculation. You don't have to. Okay. If you don't do this, you're converting your milliliters to liters to kilograms. So basically everything I said orally has been typed out in statements. Okay. Anytime in chemistry 20, when you're told there is a solution, we will not tell you it's water-based. You're going to assume that. So you have a sodium chloride solution, it's in water. Okay. If something was in methanol as a solvent, we'd have to tell you. Okay. You have 1 gram of ethanol in methanol. Okay. So that comes up a lot. Okay. That the solvent is not stated. So this is going to be a question for you to work on. I'm just going to help set this up a little bit. So the first one you're going to do is tell me what the part per million and part per billion. So you're going to have to do some unit conversions for 25 milligrams of sodium ion in a maybe typical water bottle, 355 mils. And then second, 500 nanograms of calcium, okay, in a tiny little bit of water, okay, about a 1/4 milliliter of water. Now I'm going to remind you of those prefixes you have on page 3. You can look at those, but I'll have the conversion up. So I put mega, kilo, a dash for the base, milli, micro, and nano. When you're going to smaller units, you're going to do things in littler and littler pieces. You multiply by 1,000 for every jump. When you have to go to a bigger unit, that's when you're going to divide by 1,000 for every jump. So if you have nano and you need to go up to micro, that is 1 jump in your table, so that'd be a divide by 1,000. If you had to do 2 jumps, that's divide by 1,000 twice, which is not divide by 2,000. It's divide by 1,000,000. So we'll recap these answers and talk about kind of shortcuts for doing parts per billion after you've completed A and B. Okay. So I'll put up parts per million, then parts per billion, and then we'll compare the two. I'm not going to show all my work. So I ended up doing milligrams per kilogram for parts per million, 25, that's given. The water, I went milliliters to grams, and then I had to divide by 1,000 to get kilograms. So that gave me 70 parts per million, rounding to the second number. When I did parts per billion, I did micrograms per kilogram. So I had to go from milli to micro. So milli to micro is going down a jump. So it's a multiply by 1,000. So that's 25,000 micrograms, and the kilograms are the same as the parts per million. And I got 70,000 parts per billion. Now, I actually, once you kind of realize the difference between million and billion, you don't even have to bother doing the math. Parts per billion is always 1,000 times bigger. Okay? So you can get through Chem 20 by just learning parts per million and multiply by 1,000. Okay? We had 70 when we expressed it in a million parts. We had 70,000 when we expressed it in another 1,000 parts smaller. Okay? And this is always true. There's always 1,000 times difference between the two. Okay? So if I had 10 parts per million, that'd be 1,000 parts per billion. Okay? Parts per trillion is just multiplying by 1,000 one more time. So with B, you could do million and billion, or just do parts per million and multiply by 1,000. So I'll give you a minute or two to finish that up, and then we'll recap that answer. Okay. So there's many possible units you could use to solve B. I'm going to use slightly different ones. Anything a million in the difference will work. So I ended up using the base and micro. So the base and micro are two jumps apart from each other. It wasn't one of the original ones, but it works. Micrograms per gram, micros 1/1,000,000th. Okay. To convert nano into micro, that is one jump up. Nano up to micro. And I'm going up, so it's divide by 1,000. Then I need grams on the bottom, because that's a million times bigger than micrograms. Now, milliliters and grams are directly interchangeable. No, most probably didn't pick this unit. Most probably went to milligrams per kilogram, possibly. Okay, maybe you didn't these units. You can do this many ways, but the ratio should always work out to a little under 2, 1.97 parts per million. So if you did different units, you know you're good if you got around 2. No, parts per billion, I'll do it the short way, the way that's kind of the fastest, most efficient on a test. Okay, it's always multiply by 1,000 to go from million to billion. So that's 1,970 parts per million. Okay. We're not doing parts per trillion, it would be 1,970,000 parts per trillion. Okay.